Hey everybody, tonight we're trying to show this huge number on the left-hand side, which is the summation of a bunch of factorial terms, leaves a remainder of 3 upon division by 10. Now let's just briefly review what we mean by factorial. 6 factorial actually means to multiply all the integers less than or equal to 6. So that's 1 times 2 times 3 times 4 times 5 times 6. Okay, when you multiply that out, it's equal to 1, let's see, 720. 1, 2 times, that's 120 there, and then 6 times 120, that would be 720, right? Okay, so that's what we mean by factorial. We're supposed to show that the summation of the first 679 factorials actually leaves a remainder of 3 upon division by 10, okay? Now, let's take a look at some useful facts here. And this involves a little bit of exploring. I just did 1 through 4 by hand. It's not so hard to do. This would be 2 factorial right here, which is certainly 2, 3 factorial. 1 times 2 times 3 is 6, and 4 factorial. And when you sum those values up, you actually get 33, which is really a big part of what we're trying to prove here, okay? So this is straightforward enough. Just the first 4 of these terms sum up to 33. Okay, but we're supposed to sum up the first 679. Well, fortunately, there's a nice labor-saving device here. Any n greater than or equal to 5 is going to result in a factorial that's congruent to 0. That's not too hard to see because 5 is present. In other words, n factorial would be able, you could rewrite it as 10m for some integer m. And the reason is, if n were equal to 5, you would have 1 times 2 times 3 times 4 times 5. So there's certainly plenty of even numbers to go around. And then you have 5. So 10 is equal to 2 times 5, right? And the same kind of thing is going to happen for any number greater than or equal to 5. For example, 6 still will have 5 in it, all the 2's you need. 7 factorial will still have 5 in it, all the 2's you need. Once you get up to 10, you have 2 5's. And so this is just kind of a very weak statement right here, actually, but it's all we need. So for any n greater than or equal to 5, we have n factorial is congruent to 0. Okay, so let's re-examine the original. Here's our original expression. We're supposed to show that it's congruent to 3 mod 10. But notice that 33 is certainly congruent to 3 mod 10. So we'll replace the equal sign with 3. And again, that's because 33 is equal to 3 times 10 plus 3. So 33 is congruent to 3 mod 10. All right. Now all of these over here are successively going to be congruent to 0. So I'm going to go plus 0, plus 0, and we'll just do ad infinitum. And there would actually be, let's see, y'all, 679 minus 5 is 674. But you have to add 1 if you're familiar with the summation operations. So this would be 675 times here. But we don't care how many times because they're all zeros, right? Just being emphatic about how valuable that particular result is. The in factorial for n greater than or equal to 5 is always congruent to 0. Okay, so, and this is mod 10, of course. This is clearly modulo 10. Because all the build-up results have been mod 10. So that proves it, folks. It is congruent to 3. Fairly easy problem as long as you have, you know to explore. It did require a little bit of explanation or exploration. If you take a look at this, folks, it's not evident just by looking at it initially. So you have to explore, you have to investigate, you have to look at some special cases. And this result from 1 to 4 was crucial. Then after that, any of the other terms are going to be congruent to 0, which results in this truth right here. So we proved what we set out to prove. And that's all for tonight.